Hello and welcome everyone to our fifth video of the complex number series, where we go into detail about everything you need to know for the complex number examination. And we have finally made it. We made all the knowledge, the prerequisites, in order for us to go and jump into the introduction for our complex numbers finally. And make sure, if you followed us so far, that you are subscribed to some of my social media so you don't miss any of the future courses I will be offering. So let's dive right into the introduction for complex numbers. In order to introduce the complex numbers, I would like to start with a little story. I would like you to imagine you are a farmer many thousands of years ago. What numbers would you actually need? Well, in order to count how many sheep and cows and chickens you got, all you really needed to do is count 1, 2, 3, and so on. That were all the numbers you really needed. Because once you have those numbers, all your worries are done. Now, these whole numbers, we actually call the first part of our numbers the natural numbers. These are the counting numbers starting at 1. Well, that's not quite right. Sometimes it starts at 0, sometimes starts at 1. Let's have a look here. Our natural numbers, the counting numbers, are going to have a symbol with an N, with a double line, to show us what numbers we have here. These are the natural numbers. Now, the problem here is that even up to today, after thousands of years of counting sheep, mathematicians still don't know, is 0 a natural number or not. About half of the mathematicians in the world are convinced that 0 is one of our counting numbers, our natural numbers, whereas the other half is arguing straight against it. So sometimes you will see people using a plus next to the natural numbers to indicate that 0 is truly part of what their counting numbers are. In my opinion, 0 is a counting number, so I will be using 0 in my natural numbers when I talk about them in the future. Let me know in the comments, do you think 0 is the first number in our counting set, or should we start counting at 1? Now back to our farmer situation. When we look at our animals, we can count, and it's clear that we can start at 1 or maybe 0 if you don't have a cow. Then all your worries are done. However, once we think about money, right? You need to pay for the cow at some point. So what if someone doesn't have enough money? What if you needed to pay 10 gold coins for your cow and you only had 8? Where does that leave you? Well, that leaves you with debt, right? You need to give someone more money back next time. So if you think about this, how could you describe this in terms of numbers? So mathematicians will, at that point, will have had some debates on if this is actually something that we want to have. But negative numbers at that point were not part of the numbers people were talking about. But clearly with debt and other parts like this, we do need negative numbers. So we're going to introduce the next biggest set of numbers. In the past, people now needed negative numbers to, for example, represent debt. Someone might have -1 gold coin. That means they have 1 gold coin debt. So at that point, we have now all of our counting numbers and the negative versions of them, as well as 0. And we represent this with a little z. This is called the integers, or the whole numbers in general. Well, now let's have a look at what else this farmer can do. He's now dealing with debt. He's counting all of his chickens and his cows. But at some point, he's going to realize there's only 1 cow left. But he's got 2 customers who both want the cow. Well, what can he do here? Not trying to be cruel to our animals, but there's one obvious solution how he can serve a cow, or at least part of it, to each of his customers. He can cut this cow in half. Well, if he does that, what does that mean in terms of our numbers? We're going to have half of a cow. So in reality, we can have more than just our whole numbers. We need to expand our number set to also include half, a third, a quarter. Think about the farmer going home after a long day of work and his wife has cooked a meal and made a cake. If I split this cake amongst the 5 family members equally, then they will get a portion of the whole, maybe 1/5 of the cake. So in reality, there's lots of ways that we can split things in reality that includes our fractions. So at some point, mathematicians said we need to include our fractions into our numbers because they actually represent something in reality. We call these numbers our rational numbers. The rational numbers have a Q with a line through it to represent their set. Now over here, I would like you to realize that every time when I made more numbers, when I created a bigger set, I included the smaller one in the other one, in the bigger one. So what we actually have is in the middle, we've got our natural numbers, which is our counting numbers. Now our whole numbers, the integers with a z, actually come included with the natural numbers. So 1 is actually a whole number, an integer. 10 is an integer, but also the numbers that we added afterwards. So -10, -5, -8. So when we added our rational numbers over fractions, anything with a over b, where a and b might be integers. So here we actually include all of the other numbers as well, because think about 4 divided by 2 is actually 2. So our fractions are not just an expansion, they also include everything else that we had before. And now here's the other part. We talked about irrational numbers and how they are so different from our other numbers that we've got so far. So the irrational numbers have a bit of a funny way of being represented. It's all of our real numbers, which is the R, without our rational numbers. The line kind of means without. So here at the bottom, we have all of our irrational numbers. And now these are separate, not including the others, because our fractions are not irrational numbers. Remember, irrational numbers have infinite many decimal points and they're never repeating. Well, our fractions have exactly those repeating parts, so they can't be an irrational number. Here I've got a few examples. We already know the square roots. We briefly mentioned pi and e being an irrational number, and I've put in phi here as well, one of the constants for the golden ratio. You don't really get to see this in high school, but Google this and see what it comes up with. Okay, now all together, all of our rational numbers and our irrational numbers all together, this forms our real numbers. All the numbers that you had available to you your whole life. You've done your calculations, you've had fractions, you've had surds, you've had the pi value, e values, everything like this. However, unfortunately, we're not done. Let's have a look at this equation here. We have x squared is equal to -1. What are the solutions to this? Well, we have a squared, so let's take the square root on both sides. Then we get x is the square root of -1. Here we have a problem, and this is a problem that mathematicians have for a very long time been fighting and said this is not going to work. You can't take the square root of a negative number. Well, think about it. Which number multiplied by itself gives you a negative? Well, if we take a positive number times a positive number, because it's the same number, is going to make a positive. If we choose a negative number, we multiply it by itself, well, that's also negative. Negative times negative is going to be a positive number. And clearly 0 times 0 is also not going to be -1. So which numbers could possibly multiply together to get you a negative number? This doesn't seem to be possible, and it's not possible with the numbers that we have so far covered in this course or in general in your mathematical career so far at high school. So now we're going to actually invent this number and say, well, I don't know what it is, but there is this number. If I multiply it, it should be -1. So x is actually I. So I is the imaginary number. We're going to just say that I is the square root of -1, and if you square both sides, you get that the square of I is -1. This is the defining property that this number I has. That is everything that we need to describe this number. Now, why don't we write it in numbers or anything else? Why is it with an I? Well, we could have written any kind of symbol like we used to for our numbers. We could have used any symbol for this, but we chose this I. Imaginary number is actually a very bad name. This number is not as imaginary as you might think. It actually exists. It's not something that we just make up and it's this abstract concept. This number is actually real. Well, that's the problem. It's not real because it's not a real number, but it exists. That's why we have so much problem thinking about our real numbers and what do we call them? And the only thing people came up at that time, and it kind of stuck, is the imaginary numbers, because they weren't quite real. Okay, now enough talk about how we kind of got to our number system, what we're going to do. Let's have a look at the complex numbers, their properties, and how we can deal with these together. The first rule that we're going to talk about is that a complex number is z is equal to a plus bi, where a and b are real numbers. So we're going to have a real number plus a real number times I. Just like the irrational numbers, we had a times the square root of b plus c. We now have a plus bi. So we need more information. So I'm going to give you all this information now. Screenshot these rules afterwards if you need to, or check out our courses in the first link of the description. We have free courses where all of these videos are nicely structured. You've got your own login and you can get back to where you were. And we also have premium courses where all of these rules are put into flashcards for you, so you never forget those. Make sure you're having a look. Okay, let's have a look at our second rule. We have z is equal to a plus bi. A is here called the real part of a. There's no imaginary part multiplied to it, so that's just a real number. That's why we call this the real part. Then b here is called the imaginary part of our complex number. And we write this as re of z, which is the real part of z, and im being the imaginary part of z. But be very careful, and this happens all the time, so make sure you start right from the beginning. The imaginary part is not including the I. So even though our complex number is a plus bi, the imaginary part is just b, whatever you've got in front of the I, not including the I. So we're just going to go through some examples so that you can get more comfortable with the terminology and what we have. Here we have our complex number 5 plus 2i. Well, what are the real parts and what are the imaginary parts? The real part is 5. The imaginary part is the number in front of the I, so that's 2. Okay, we've got w is minus 2 plus i. What is the real part? What is the imaginary part? The real part is the one with no I, so that's minus 2. And the real part, the imaginary part here, well, what is the number in front of the I? Well, the coefficient multiplying I is 1. So the imaginary part here is 1. What about u? U is 2. So what is the real part? What's the imaginary part? So the real part here is 2. It doesn't have an I. And the imaginary part, well, if there is no I, it must be 0. And this comes back to how everything worked together in our picture. So every single real number is by definition a complex number. It just does not have an imaginary part. So let's have a look at the next one. What about v being 4i? Well, what's the real part? There is no number by itself, so the real part is 0 and the imaginary part is 4. Hopefully, after these examples, you're a bit more comfortable. What is the real part? What is the imaginary part? Because we're going to need this in our next part. Let's have a look at this. The rule set, we can draw the Argand diagram, which is basically the coordinate system that similar to what we've had before. But on our horizontal axis, we no longer have x. We put the real part of a complex number. And on our vertical axis, we put the value for the imaginary number, just like in this picture above. So let's have a look at our first number. Z is 3 plus 2i. We know that the real part is 3 and the imaginary part is 2. So how would we put this into the diagram? Oh, actually, we're going to give you 2 more, W and U, and you can check out the real and imaginary part here. Make sure that you're comfortable finding these for all sorts of complex numbers. Let's have a look on what we are going to have at the bottom. Well, we are going to have a look at Z first. Z was our complex number with real part 3, imaginary part 2. So we're going to put this as coordinates 3, 2. The real part first, just like we would do on the X and Y axis. Now have a look through, pause the video if you need to, make sure you're familiar with how to find the real part and the imaginary part, and make sure that you can get to these in the diagram just by using the coordinates. Remember, the first part of our coordinates is the real part, the second part is the imaginary part, and there's no I, so we can just chuck this into this diagram. If you're familiar with this and you're happy with this, we're going to have a look at our next rule. So representing a complex number in the form Z is equal to A plus BI with real and imaginary part is called the rectangular form. This is one of the 2 standard forms that we use all the time for complex numbers. So there's 2 more things you need to know. Purely imaginary means that our real part is 0. So if our complex number is purely imaginary, only imaginary, then surely the real part must be 0. And also, if it's purely real, that means our imaginary part is 0. So in the end, we just have a real number. So with all those rules, I hope I have not overcomplicated the first part of our introduction. There's lots of new things. Make sure you are learning all those rules and check out, as I said before, our course with all of our structured processes. You've got your own login to save your process and the extra services that you can have a look for, where we have rules as flashcards and extra practice examples for every single video. I will see you in the next video where we are going to be tackling lots of the operations with complex numbers, and I will see you there.